Hey data junkies, welcome back. We're continuing our adventure into the land of multiple linear regression. In the previous video we did the setup foundations for how to use dummy variables and reference groups in multiple linear regression, MLR. And now we're going to go ahead and do a video on looking at another example of using these dummy variables, and we're going to pull some data from R and see how this works in particular. So let's go ahead and jump into this. Now, in using this particular data, we're going to rely on the General Social Survey from 2016, and I'm going to start with some recodes. We're going to break out some recoding, make ourselves some dummy variables, and then we're going to show you different ways we can plug them into the regression in order to obtain these reference groups. The first variable up is happiness in marriage, and we're going to use both a recode and an if-else approach to kind of show you how you could do it with either strategy. So when I look at happiness in marriage, which is coded as hatmar in the data, hatmar is a factor variable with 3 levels. The structure function doesn't tell me all the levels, so let's take another closer investigation. I'm going to run a table function. Oh look, I have very happy, pretty happy, and not too happy, with the spreads heavily favoring those that are very happy, and very few people are not too happy. So as far as the data goes, it's a little unbalanced, but as far as life goes, I'm glad to hear it. So last, I'm going to take a look at the levels. The levels function is the one that's going to tell me the number coding, that if I was to turn this into something that's numerical to plug into the regression, how is R going to see it? And what I have is 1 is very happy, 2 is pretty happy, 3 is not too happy. Now when I want to go ahead and make these into dummies, I can at most make up to 3 here if I'm doing 1 category per dummy. So I'm going to use the recode variable first. This is in the car library, and I'm going to be able to make up to 3 of them here. So in each one, I'm going to make a new variable, and in this case, I'm calling it hatmar dot, and then a word that just kind of indicates which one I'm looking at. So I'm going to have hatmar dot vary, hatmar dot pretty, and hatmar dot not for the very happy, pretty happy, and not too happy. For each one, I'm going to start with the same basic code approach, calling the recode function, followed by an as.numeric with hatmar. I could use the text label names of very happy, pretty happy, and not too happy, but it's so much faster to just pull up the code and say turn hatmar into a numerical value and then recode those numbers, especially since the output value of these dummies I want as 0, 1 anyways. So what I'm going to know is I remember that very happy was code value 1, so in my recode, and I'm going to specify 1 equals 1 for my very happy dummy. Then 2 will be 0, 3 will be 0, meaning not pretty happy and not too happy are going to be combined together as my 0 group. So my dummy variable for very happy will be those that are very happily married compared to those that are not. I'm going to repeat this process with pretty happy, but when I get to code value 2, that's going to be my indicator, so that's going to turn up to 1. Very happy and not too happy are going to code out to 0. So the dummy variable for pretty happy is going to be those that are pretty happily married compared to those that are not. And I'll repeat the same process again with hatmar. So it's a nice intuitive way to make 3 indicator variables. Let's go ahead and see this again using an if-else approach. This is good for those of you that don't have access to the car library or are just simply more comfortable and like using if-elses. Here we have the exact same strategy. I could have also done an as numeric version on here, but I chose to use this one just as the original text so you can also see a difference on how some of these coding approaches work. So in the looking at the very happy up at the top, I start with my if else and I say if else if hatmar is to very happy, make that code 1. Nest another if else if hatmar equals pretty happy, make that a 0. Nest another if else hatmar equals not too happy, make that a 0. I've now combined pretty happy and not too happy into a 0 group. And then I close it out with an NA, meaning if you are not identifying as very happy, pretty happy, or not too happy, you are missing. It's always important when you're doing your if-elses and any other recode that if you have a bunch of missing values, you need to account for them. Don't accidentally turn missing values into active values because of a botched recode. So you're going to repeat that process for pretty happy and not too happy, and I've got the variables named for the dummies the exact same, so no matter how I do this, they would come out to the same values. Always, whenever you can, go ahead and check your recodes. In this case, these are low categories, so they're really easy to check with a bivariate table. So I'm going to run 3 different bivariate tables, hatmar in each one, and then the dummy variable, each new dummy variable I created in each of the bivariate tables. I have the results on the screen here, just kind of giving a quick overview. It doesn't quite show how it would look in R, but this is a cleaner printout. And what you're looking for is to make sure that your dummy variable has coded the group of interest as 1 and the other groups of interest as 0, which is what it looks like it did just fine here. Now, on the screen here, you're going to see a mess of code. Don't worry, don't get overwhelmed. I'm right here with you. So, now what we're going to do is we're going to recode race. And in the GSS, we have a variable called racen1. Racen1 has 16 different racial and ethnic groups. And we can see those with the levels function. Now what I could do is make up to 16 different dummies here, but what I want to actually do is I'm not so much interested in the granularity levels offered, so I'm going to combine some of them into higher level racial and ethnic groupings. Then I'm only going to need a few of them. So here I'm creating 5 0-1 dummies. I'm making dummy variables for whites, blacks, Hispanics, Asians, and others. And I don't mean to be insensitive by just broadly categorizing some of these and the names I'm choosing for them. I'm using names that are just colloquially used in common survey research today. So in this particular case here, in the first one, I'm making the dummy variable for those that identify as white. So again, I'm using the recode function as numeric on racen1. And in the code, I'm doing 1 equals 1 because level number 1 was white. And then levels 2 through 16, I'm coding as 0. So this is going to make a dummy indicator for those that identify as white compared to all other racial groups. And those that identify as black or African American, I'm using the same code setup, but when I get to the code values, I'm using 0 equals 1 because these are the whites. They're now in the non-indicated group here. 2 equals 1. These are the blacks and African Americans. They are now a code value 1. They're the group of interest. And then 3 through 16, all of the other remaining values, code value 0. Now I have a black dummy saying that it's a value of 1 when someone identifies as black or African American, 0 if they identify as any other racial ethnic group. I'm going to repeat the process with those that identify as Hispanic. That's code level 16. I'm going to repeat the process with those that identify as Asian. And this one, it's split up a little bit. So code values 1 through 3 are 0. And then 4 through 10 are a wider variety of racial ethnic groups that I am merging together into a common Asian ethnic group. And this is going to compare things like Asian, Indian, Chinese, Filipino, Japanese, Korean, Vietnamese, and other Asian. If I wanted to make it a little more granular, I could pull Asian Indian out and maybe make that more of a Southeast Asian type of dummy variable. But in this case, I'm making it a broader context of Asian. And then other, I'm pulling out all those other groups who did not identify as one of the 4 up above. They're all getting coded into 1, and the others are getting coded into 0. Now I'm going to do one more recode here, just because I want to show you how some of these dummy variables can work inside R. So in this case, we are using the same racial groups, but instead of making 5 separate dummy variables, I'm making one race variable with 5 levels. So you can think that we're taking racen1 with 16 separate levels, and we're just combining it down into one variable that has the same 5 levels I worked on before. So in this case, my recode is going to do the same racial combinations, but then once it's a numeric variable, I'm going to turn it into a factor variable that's going to have ordered levels and labels on them, where the labels correspond to the racial groups: white, black, Hispanic, Asian, and other. I could have nested this all together in one code, but I broke it up into 2 just so it looks a little more clean in both my code and on the screen for you when you're reading it. Now that I have my happiness and marriage variables and I have the race variables, I'm ready to go ahead and plug them into my regressions here, and we can take 2 different approaches. The first approach is to let R just auto-select the reference group for you. The second approach is letting you choose which one you want to be your dummy. Now, which approach ever you're going to do, keep in mind the reference group is the one that is omitted from the regression model. Okay, so when we go ahead and let R do it, this is what I call an auto Recode method because it makes a one-time list of dummies for that variable. And the way you can do it is if your variable is a factor, like our race5 variable is, you can just use it as is. Plug it right into the model, and it's good to go. If your variable is any other type, like maybe a character, or if you have values that are already coded as numbers, because that's how the data set came, or that's maybe how you did some of your recoding, but you want to use it with this auto-factoring method to make your dummies, then you need to wrap that variable in a factor term inside the regression. I'll show you what that looks like in a moment. And what this is going to do is this is going to make dummy variables for you without having to do any of the dummy variable recoding, and it's going to grab by default the very first, the lowest number category of that factor. Okay, you really don't get to choose which one it's going to be at that point. It's just the first group and it goes with it. Now, a word to warning, there is a function out there, and if you're on some of the internet boards like Stack Overflow, you're going to see a option there where there's somebody using a re-level function. The re-level function, you can use this on your variables and on your factors in order to help choose which one you want to be the reference group. But you have to be careful with that because what it's actually going to do is it's going to change the ordering of your factor variable to make that new reference group the lowest category as it counts in order up through your factor. So if that's an ordinal group, it could throw things off. All right, so keep that sort of thing in mind. Nominals doesn't matter as much, but it can throw off the ordinals and other dummy groups depending on how you have them coded. And if you want to use the other approach, the one where you get to choose, well, we up above made a whole bunch of dummy variables by hand, and you get to just plug each one of them in, one by one, into your regression model, leaving one of them out as the reference group. Just leave out the whichever one you want, and that's the one that'll be the reference group. You have much more granularity and control when you do it this way compared to the auto dummy method on the previous slide. So the dependent variable we're going to use here is looking at opinion on your family income, and that's a variable called FINRELA. And FINRELA is a 5-category Likert type scale variable in which we're asking someone how do they believe their family income is, and if they think it's somewhere on far below average all the way up to far above average, where high value is meaning you believe you're much better than the average family income. And I want to see how does your race and your marital happiness help predict your sense of your family income. So let's go ahead and get it fired up into a default regression equation where I have the opinion on family income is equal to my y-intercept plus my coefficient times marital happiness plus my coefficient times race. And this is good if these are racial categories, but if I want to show what it's going to look like with all the dummy variables minus the reference groups, then what I'm going to have is the opinion on family income equal to my y-intercept plus my pretty happy and not too happy variables plus black, Hispanic, Asian, and other. And I've left out Asian and, very happy and white, where these are my reference groups. So plugging this into a ready to go for our equation, this is the one where we're going to specify by hand which one we want as our reference group. So here I have, and I'm saving my regression as an object, so I'm doing the linear model on an as numeric of FINRELA. That's a 5-category ordinal, so I can go ahead and turn this into a numeric. And then I've used each of the dummy variables, Hatmar pretty and Hatmar not, black, Hispanic, Asian, and other, as all of the dummies going into the model, calling them from the GSS dataset. I've left out, intentionally, race.w, which was my dummy group for whites, and hatmar.vary, which was my dummy group for very happy. They will each become the reference groups. I've chosen them in this particular case because when we get to the auto factor method, these both happen to be the first categories of their particular variables and were pulled out as the reference groups. And I want to be able to show you the comparisons between this regression output, where we are specifying which reference group we want, to the one that does the auto dummy. So here are the regression coefficients of what we're looking at here. And so we can see that, for example, those that identify as pretty happily married compared to those who are very happily married, pretty happily married will correspond to an average 0.9 rank decrease in your opinion of family income, controlling for all other variables in the model. This is statistically significant at least alpha 0.01. I can tell that because it's got the 1 dot on the far left side and the little cheater codes. If I was going to go ahead and look at those that were not happily married, we have negative, I'm sorry, let me start at the beginning. Those who are not happily married correspond to an average 0.4 negative rank group decrease, negative 0.4 change in the opinion on family income. One more time here. Those who identify as not happily married correspond to an average 0.4 rank decrease in opinion on family income compared to those who are very happily married, controlling for all other variables in the model. Got it on the third try. So then if I was to look at the 4 racial dummies, I have black, Hispanic, Asian, and other. Those who identify as black correspond to an average 0.37 rank decrease in opinion on family income compared to those who are whites, controlling for all of the variables in the model. Those who identify as Hispanic are 0.66 ranks less on average compared to whites, controlling for all the variables in the model. Those who identify as Asian are 0.3 ranks more than whites on average, controlling for all of the variables in the model. And those who identify as any other race, meaning not black, Hispanic, Asian, or white, have on average 0.36 ranks less than those who identify as white, controlling for all other variables in the model. And if you're wondering, are these meaningful changes or not, some of them are around a thirds here. That means a Likert scale of 1 to 5, a third of a point means it will move the dial about 1/3 of the way towards a 1 point increase on change. Not a huge jump considering that these are one impact changes here. It could contribute somewhat considering these are all statistically significant, but maybe not in a huge meaningful way. None of them are doing at least a 1 rank change according to happiness in marriage and your racial groups. Let's go ahead and run this exact same regression again, but instead of using the dummies that I get to pick one by one, I'm just going to specify as numeric on FINRELA for the opinion on family income, and then I'm just going to plug in HAPMAR plus race5. These were already coded as factors in the data, so because they're already factor types, I can use them as is. So when I do that and I run my summary on that, keep in mind whites and very happy are going to be the reference groups here because they are the first value code in the factor. And when we check these regression results, they are the exact same values as we did when we specified the dummy approach previously. The only thing that's different is how the data is named on the variables under that coefficient side there. So when we first had them, they had the names of the dummy variables we had, such as hapmar.pretty. Here it says hapmar pretty happy, and it put the P on pretty all the way up against the R in hapmar with no spaces. So it's a little more difficult to read, but it's there. Hapmar.not was my dummy for not too happily married, and here we see hapmar not with no space, too happy. So what it's going to do here is it's automatically going to create the dummies for me, pulling out the first one as the reference group, and then it's going to, under the coefficients name, it's going to write the name of the variable as you have it, and then immediately thereafter, with no space, write the name of that particular level as that group. So we can see race 5 black, race 5 Hispanic, race 5 Asian, and race 5 other, with no spaces in between the 5 and the B in black, H in Hispanic, A in Asian, and so on. Okay, so this is a slick way to go ahead and use this as long as you're okay with having the very first group pulled out as your reference group. And also keep in mind, if your variable names are very long, they may either truncate in your regression output, or it's going to cause this large wraparound, and so it might make it a little more difficult to read using this particular approach. The last one I'm going to show you here is using the same auto factor if your variables are not factors. Now in this case, hapmar and race5 are already factor variables. Putting a factor function on them is not going to hurt the variables themselves. But we could use this just as a brief example. If these were happen to be coded, let's say, as characters, this would work out. So let's go ahead and put factor on each of these variables here and see how it works. Now I'm going to get the exact same regression coefficients again. Nothing's going to change between each of these three methods. But what's going to change in this case is when we look at the factor names under the coefficients to see the variable names, now it says the word factor because we put them in the factor function. It's going to wrap the variable name in parentheses that it is factoring, and then outside the parenthesis, it's going to list the name of those different reference groups. I like this approach a little bit more than the previous one. First of all, because it's already popping out right away and says, hey, this is a dummy variable. Something's been pulled out as the reference group. So if you're not sure, you see it out immediately. The parentheses also help make it a little bit more readable when you're looking at your variable names, whereas the factors you plugged in automatically just smushed the level up against the variable name, makes it a little harder to read. So this just makes it a little bit more clean, and you're getting the exact same results either way. So that's going to go ahead and pull up all of the different ways we can do these dummies variables with regressions and how you can interpret them. Putting up here the regression diagnostics. We're going to look at these real quick just because it's good for you to get this exposure here. So in the upper right, these are our residuals versus leverage. This is where we're looking for changes in linearity and homoscedasticity. And what we have up at the top is the data looks somewhat dispersed out. There's a little bit of a slant to it, so there does appear to be some sort of patterning going on here. I may have some heteroscedastic effects, but the line is mostly linear. There's a little bit of a shark fin popping up. Not too concerned about it at this point. It's doing pretty well. Top right, we have the normal QQ plot. This is where we're checking for normality, and we see this sort of staircasing effect as it goes up. This is partially an artifact because our DV happens to be an ordinal variable, so it's not a very clean continuous scale. But for the most part, it's kind of tracking along with the normality line there, and our tail ends at the far left and far right are doing pretty well against that line, so I'm not too concerned. The lower left is our scale location. This is where we're looking for that heteroscedastic effect. You want to see that the data points are just scattered randomly, that shotgun buckshot sort of effect. And here, I'm starting to see a pattern. These start to look like these little zigzagging effects chasing down in a couple columns here. And that definitely looks like some sort of geometric forms are starting to appear. So I may have some problems with heteroscedasticity that may need to be investigated by my variances. And then down to the bottom right, this is the Cook's distance, the residuals versus leverage plot. This is the one that's checking for influential outliers. There are no red dotted lines appearing in the upper left or lower right of that plot, which is where the Cook's distance thresholds are. And so there's no concerns about influential outliers here. And that's going to go ahead and wrap up this little exercise video I have for you. I'll see you all next time where we start talking about multicollinearity. I'll see you then.